Hello, everyone. I'm Michael. I'm a postdoctoral researcher at the Technical University in Delft, and today I'm going to talk about lightweight relations. I'd like to start with a disclaimer here. I know that you guys at Oracle, you all love databases, but this talk in particular, it's not about relational database management systems. Rather, I'm going to talk about how we can equip collection libraries with sort of lightweight relational data structures, and that by not adding another type, and by saving dramatically memory. And that's like 5 times over comparable approaches. Let me reiterate some of the properties that we expect from collection libraries. First of all, collections contain commonly used data type abstractions, like lists, sets, or maps. And for all these abstractions, you usually have a handful of implementations that are highly optimized, that are typically generic and general purpose, and they are not tailored towards any particular workload. And in order to fulfill that, they have to carefully balance memory and runtime characteristics, so to be versatile and yet scalable, so that you can throw like a variety of different workloads at them. Coming back to relations. Well, graphs and many-to-many relations, they occur in many areas in computing, for example, in compilers, runtime of programming languages, or program analysis. And one example that many of you are, I guess, familiar with is control for graph analysis, where you have the basic blocks in the code encoded as nodes in your graph, and the possible flows of control are encoded as edges. Well, talking about relations, there's nothing else than a binary relation from nodes to nodes. And how would you go about implementing that with a collection library? Well, we have maps and we have sets at our disposal, and they are kind of universally present in all these libraries. So what we can do is we can just nest sets as the values of a map to then model all the successors of one node in the graph. So while maps and sets are universally present in all these libraries, there are some languages or libraries, like language-wise Scala and Clojure, or libraries like Google Guava, that provide nicer API abstractions for that, so that you have, for example, a dedicated multimap data type instead of having to do the composition yourself. Well, and in Scala, for example, you can use built-in traits in order to lift a map with nested sets to the API functionality of a multimap, and idiomatically in protocols, you could use something like, in Clojure, you can use something like protocols. Well, that's just on the API side, because all of these examples that I gave you, they still internally use an explicit nesting of sets that are nested as the values of maps. And there are some particular painful properties of that explicit composition. So one of it is that the runtime performance is suboptimal. And I would like to just flash you some code. You're not supposed to read it all in, how you would implement, for example, insertion in a multimap with Clojure's data structures. So there's already some optimizations involved, a lot of like dispatching, case distinctions, even dynamic type checks. And it doesn't get easier with delete. Another thing that bothers me, for example, about that explicit composition is that they come with a really high average overhead. So in Clojure and Scala, for example, you have on average a 65-byte overhead per stored key value pair. And if you think about it, that's quite a lot. If you just want to store 2 references, like the key and the value, you end up with having to store 8 times more in accidental encoding. And even worse, the explicit composition can lead to severe algorithmic limitations. And in order to illustrate that, I will use immutable collections as an example. But what I'm going to talk about later on, like in the solution space, likewise applies to mutable collections. Well, in immutable collection libraries, you often find some sort of builder abstractions. And builder abstractions are used to efficiently stage the initialization or creation of immutable object instances. So here we see, for example, a map builder on the slides, where you can, in a mutable fashion, use several update operations, like several put operations here, before you freeze the state of the instance and then yield an immutable instance. Well, some implementations out there, they're particularly clever in how to do the conversion from the mutable builder abstraction to the immutable data structure. And in particular, for example, in Clojure, you have atomic constant time conversions from one to the other. So that's the case for regular map data structures, for example. But we are interested in multi-maps, aren't we? So if we want to efficiently stage the creation of a multi-map, well, how do we do that with builders? We can nest set builders in map builders, as we do nest sets in maps. But here you see the abstraction breaking down, because suddenly, instead of having like a one conversion, you have a linear time conversion. And that is because we first have to iterate over all the nested set builders, close them, before we then can yield our final multi-map. So what I'm saying here is, while you can compose immutable maps and sets with each other, the builder abstractions, they don't compose. Everything so far that I was mentioning, well, speaks well for why don't you provide a dedicated multi-map implementation, right? So like just engineer it from ground up and provide a data type that eliminates all these issues that we had. Well, that's something we could consider. But the question is, should we do it that way? Should we add yet another data structure to our collection libraries? Because what it entails is that you have invested a lot of like time and effort, probably money, in engineering, optimizing the data structure, and then also like maintaining that over a long time span. So, well, maybe it's not the way to go, like to add yet another data structure. And as I said before, collections, they have some certain properties that we expect from them, so that they have a small set of highly versatile abstractions. And as you saw, we can already compose multi-maps, also like they have some problems. So what would be alternative solutions to tackle that problem? Well, let me take a step back and just look at the differences between maps and multi-maps. And if we ignore for the moment all the API differences that are definitely there, like just from the memory representation, the only difference is that for a regular map, we need to store one-to-one correspondences between keys and values. Whereas like for multi-maps, we need to cater for multiple values that can be associated for a single key. So another possible solution we could think about is, well, instead of having two implementations, a dedicated hash map and a dedicated hash multi-map, why not having one kind of like hybrid data structure that can adopt to its content and like, well, be a hash map and a multi-map at the same time? Well, could be feasible, but what we would expect from that is, well, if we use it as a map and like repurpose it with a map interface, that it then behaves the same as a map, like in terms of runtime characteristics and space characteristics. And well, what would you expect like from it being a multi-map? Well, that it's at least better than doing the explicit composition of nesting sets in maps. And that's exactly what I'm going to present in this talk. The Axiom hash trie map data structure, which is a two-in-one data structure. So instead of adding yet another data structure to your libraries, well, you could think about replacing a hash map, for example, to get the best of both worlds. And the core idea behind the data structure, so on the slides you see, coming back to our control flow graph example, is to canonically store in an efficient way all the data in its most effective form. So if you have one-to-one correspondences, we just store it as a key and value tuple. And if it's really like, if we really need the multi-map capacity, we can associate, for example, a nested set to that. So let me talk a bit more about Axiom's design. And in order to do so, I would like to start with a data structure that we all hopefully know, a Java util hash map. In a Java util hash map, well, you have internally one large, potentially large continuous array of key value tuples. And how would we, for example, start out and add a multi-map, let's say, feature to the data type, and that in a type-safe manner? Well, one way we could do that is adding yet another array, like that's differently typed, so that we can associate keys with sets of values. And then we can make like the case distinctions in order to store it in one or the other. Well, but the data structure I'm going to talk about, the Axiom hash trie map, as the name already suggests, is not a flat array. So instead, it's a very shallow prefix tree. And in my last year's talks at the JVM Language Summit, I covered some of the basics of the data structures. So for now, all you need to know is, instead of like having one large continuous hash map, we chunk that up in small fixed size hash tables. And because we arrange that in the tree, well, we also have to maintain references to subtrees. And we can add that by, for example, adding yet another typed array to our nodes. All right, everything we did so far is just like extending our basic data structure and adding differently typed arrays, and then creating a tree out of that. So that doesn't look efficient at all. And I completely agree, that's not efficient if we would like have that many indirections and there. Well, but from literature and from research for sparse prefix tree data structures and hash tables, we actually know how we can efficiently optimize that for sparse data as a hash table. So instead of the complex structure you saw before, we just turn all the different arrays into typed slices that just store the same space. So how's that done? Like, to give you some intuition, we have to associate some metadata with that nodes. And that's here in the form of a bitmap of type long, where we use chunks of 2 bits for indicating the type of a slot. And in our case, that can be either like it's empty, so we use that later for compressing away like the empty slots. Then we can distinguish 1-to-1 and 1-to-n mappings. And last but not least, we can reference subtrees. And with that information, we can permute all the elements that in the end, what we get is a data representation where we have typed slices, and while still maintaining the O1 lookup properties of a hash map per node. Well, that's about, let's say, a glimpse about the tree representation internally. But the collection is much more than just its internal representation. So, for example, you also need to maintain global properties and track that, like the size of the collection, so how many elements are stored there, and the hash code probably. And because we are like in a multi-map setting, if we need like the multi-map capacity, we have to store nested sets. And that nested sets typically follow like the same structure. So we have a container that has the size and the hash code properties, and internally we have then some structure that maintains all our entries. By looking at that schema on the slides, you can already spot some sort of redundancy there. Because, well, as said before, if you're interested in a flat multi-map data type, like one single abstraction for like on the API level and for the consumer, we are not interested in nested sets, aren't we? Because that's rather an implementation detail. And instead of storing size and hash code like redundantly in all the nested sets, why not just getting rid of that? Because we already know it on our top level type. So we know like the size, like how many multi-map entries we have, and also like the hash code of that. And once we do that, we can already go one step further. So now we have like an almost empty object that just, for example, redirects to the set node. So we can actually get rid of that as well and directly point from the multi-map nodes to the set nodes. So that gives us like more space savings. Well, that optimization doesn't come completely for free, because at least it requires one relaxation in the API. So the group by operation on a multi-map or a relation would need to be relaxed from returning a set, like a materialized set, to, for example, an iterable of values. And that is because we throw away like the size information that used to be a collection before. So let me talk about some performance characteristics of that hybrid data type. And we have to distinguish actually two cases. Well, I said like it's supposed to be an efficient map and it's supposed to be an efficient multi-map. So let's look at both. Well, the first thing, if we use Axiom as a map, so we repurpose it with a map API, what we get is that runtime performance is often the same as with like regular trie-based map. It's sometimes much better for particular operations, and at worst 25% slower. And the memory footprint is exactly the same. Also, we added like more flexibility to also represent multi-maps. There is no overhead that we pay. Well, let's look at how it behaves like for multi-maps. Runtime characteristics usually speed up because we have a more integrated approach, and that's due to the bitmap encoding that I showed you before. So it's on average 25 to 50% faster than having the explicit composition of nesting sets in maps. And what's particularly interesting is that we gain tremendously in footprints, or like we gain tremendously in lowering footprints. Well, how can we split it up? So if we compare that to idiomatic multi-maps in Clojure and Scala, as I mentioned before, Axiom's design already like delivers 1.7 times improvements over the other two. And in the beginning, I briefly flashed you like the insertion and deletion code of Clojure. And if you're quick, you could already spot that Clojure tries to do something similar in order like to distinguish singleton sets from like nested sets. But they do it like with having like dynamic type checks, and essentially like the map and the set data structures are not as efficient as I can get, for example, by providing a dedicated data type that does that. So the design alone already pays off tremendously. But once we then drop the size and the hash codes of the nested sets, we get even more memory savings. So that's like around 2.4x. And if we then consider something like memory layout specializations, we finally get to a 5 times improvement over what ships in Clojure or Scala. Well, so far, the design of the data structure itself. But let me talk a bit about platform support. So what would you require in order like to develop such a data structure or run that smoothly on the JVM? As I showed you before, I'm using bitmaps. And I'm using bitmaps in a very particular way. And that is like having 2-bit aligned sequencers that kind of like tag the type of a slot. Well, if we have a look at what the JDK, for example, has to offer us in terms of like bit twiddling operations, we find that there's already a lot. And that's present, for example, in the integer and long data types with operations like bit count, etc. But all of these operations, so they just assume single bits. They don't have any kind of awareness of these kind of like longer bit sequences. And that's actually something that makes it more painful to develop such data structures. Just let me give you an example in order to see what kind of operations are involved in order to maintaining the internal like state of the Axiom data structure. So on the slides, you see a 64-bit bitmap, so like just that can be stored in the long. And just assume for this example that we would like to filter and tag all the 00 sequences. Well, you see them in red on the slides. What I can use is like first applying bitwise operation or a sequence thereof in order to highlight all the 00 sequences and cancel out the rest. And once I did that, I effectively reduced the information that I need in my bitmap from 2 bits to 1 bit. And then with that, I can subsequently like use that for further processing. Well, because I reduced it, I can also think about compacting that bitmap and then going on. And especially like such compacting operations, there's nothing like present in the JDK, for example, that helps you with that. But especially for these use cases, modern CPUs already support operations or like instructions that help you with more complex masking operations and bit processing. You're not supposed to read that, actually. In particular, operations like parallel bits extract and parallel bits deposit that let you do this sort of shrinking, expanding, and much more. And for the sake of experimentation, I added that to the long and integer data types in the JDK, and also added intrinsic support in the JVM. And I would appreciate having that support maybe in future versions in order to facilitate developers who want to do more, let's say, complex bitmap arithmetics with data structures. All right, that's about platform support. Let me switch to a different topic, and that is stream processing, or more particular, parallel stream processing. As I said, we have a hybrid data type that can be like a map or a multi-map, and essentially also gracefully convert between both representations. And so the particular example that I chose for stream processing is a simple parallel word count. And that operates in a map-reduce fashion where we first emit tuples of form word and its count, and we do that in parallel, and then aggregate the counts later. If you look at the signatures and all the clauses involved, you will see that, first of all, we expect as a return type a map from type string to long. And if we then look at the collect clause at the end, we see that we first have a group by operation, a group by key actually, that turns essentially our intermediate representation, our stream of tuples, to a multi-map representation, and then does a reduction step in order to return a map. So we have maps, multi-maps involved, and we convert from one to the other. Well, let's do that a bit more visually. So let's assume our input stream is A is a character. So we have twice the word A in it. And let's assume we are now processing that on 4 different threads in parallel. So we would map the tuples on these threads and essentially get maps with singleton entries. So we just have 1 entry per map. Something that I didn't mention so far, but that's also very crucial for trie-based data structures like Axiom is that those data structures are very efficient in merging partial states because you essentially zip together the trees and that's much faster than combining, for example, 2 Java util hash maps. Well, let's do that. So let's merge together 2 intermediate results. And what we then get is 2 maps already with 2 entries. There's no multi-mapping involved. We just have 2 unique keys per map. If we then go on and merge it further, what we finally get is that our multi-map gracefully converts, or our map gracefully converts to a multi-map where the key A is present twice. And in this case, it twice maps to the integer or long constant 1. So now we did the parallel mapping and merged the intermediate results. And well, but our return type that we are looking for is actually a map. So what's left is actually doing a reduce operation. And if we are clever, we could even just do the reduce operation on a fraction of the tree. Because if you look at the sums, all the unique key entries, they have the right sum already. So we just have to reduce, in this case, 1 node, where there's 1 particular multi-map entry. And once we do that, we have the right count there, and voila, we're done. So that's just one example in how you could use such a data structure, trie-based data structure internally. But you could also implement operations like hash joins on binary relations, and so on and so on. So let me summarize what I was talking about so far. Well, first, I was introducing a data type that's a 2-in-1, so that can be repurposed from a map interface or from a multi-map interface, and that efficiently behaves as a map or a multi-map regarding the data you throw at it, and it can gracefully convert between that. You can use such a multi-map as a basis for implementing at least binary efficient relations on the JVM, and I was also showing that that kind of data structure can yield up to 5 times memory improvements over what we, for example, get out of the box with Scala. Furthermore, I was talking about some platform support that would be nice in order to engineer some such data structures in the future. And I was highlighting like what kind of CPU instructions are involved there. And last but not least, I was talking about a stream processing example, very simplified in that case, but it just highlights what you can actually do if you have such hybrid data types that can gracefully convert from one to another representation. So in total, well, what I presented today is part of a larger effort, like a research effort, where I, for example, are in particular interested in in the feature variability of collection data structures, and also like solutions and implementation choices in how to achieve a certain goal. And moreover, also I'm interested in to explore the design continuum between collections and also in-memory databases, because both of them like share a lot of things together, especially if you consider prefix-free data structures, and there is a large continuum of trade-offs to explore. Well, if you're interested to see some code, or also like have some links to research papers that go a bit more deeper and like back the performance results of the app that I was talking about, have a look at the capsule hash file collections library on GitHub. And that's it from my side. So I would like, if you have any questions, I'm happy to take them, and it would be nice to have a discussion going.
Well, just a minor thing now. I mean, in the definition you presented of the tuple, when you have the multi-map, you were talking about a set. But then in the example you show, in the case of A, you have two instances of one. So, I mean...
Yeah, right. Okay, I know what you're getting at.
So I think probably in the implementation you actually have a list, not a set. No,
Well, what you're saying is, I was talking like mostly about maps with nested sets, and then like the example that I chose uses a list semantics. It's actually highlighted as like a list multimap there. You're right. Like I was focusing on another thing in my talk. But on the implementation side, there is no difference between that, because it's essentially you just have to know which data type to allocate for nested sets. So all what the data structure does, the hybrid one that I showed to you, is to effectively dispatch between singleton instances of a collection and like collections of size larger than one. And a singleton like list can like be more or less unboxed as well as a singleton set can be, or any kind of like different nested data structure. So it's the data structure design is likewise applicable to list semantics and set semantics.
So so how you are adapting the implementation depending on what you are having at execution time?
On the long run, that's the overall idea, that you really have like flexible, adaptive data structures that really can, like, regardless of what you throw at them, like internally transform to the most efficient representation. Well, if you look at how you have to like code it in interfaces or in any kind of like type state representation, that gets like much harder. So in that particular case I would have like separate implementations for like set semantics and like list semantics, but essentially what's the only difference is internally is factory methods for what kind of container you allocate, and that's depending on the semantics. I was also showing you before the separation between the outer collection, for example, that stores the size and the hashcode property, and internally the tree structure. And that's actually also like how I can repurpose one data type with different APIs. I reuse the tree data structure like from a map API, but also from a multi-map API. And that can be like, and I can also like theoretically reuse that from a like list multi-map API, from a set multi-map API, etc. And internally I have the dispatching between singleton containers and like larger containers.
Have you done any performance on iteration or lookup and cache coherency properties of these data structures?
Yeah. So Can you get a bit more concrete, like what kind of performance? Yeah, well, I tested the performance of all these operations, and because I'm predominantly doing research in persistent immutable data structures, like my to-go targets to compare to Clojure and Scala. And I mentioned before is that like if you use it as a map that like most of the operations are the same, some of them are dramatically better, and like others are, for example, up to 25% slower. The dramatically better part is actually iteration, like as a use case, and that happens in how I can internally effectively dispatch between different data representations. And in earlier work that I also presented last year here at the JVM Language Summit, I was presenting a successor data structure to the hash map try that improves on like cache locality. And all that comes together here, and that's that data structure, like Axiom, is more or less a further generalization of the jam data structure I presented last year.
Okay, so you made a trade-off with not stuffing the hash code into the data structure to save on space.
Yeah, that's like.
But when you do a lookup from a map, you're going to have to do, when you get your value out, you're going to have to do a comparison. And often, rather than comparing all of the values themselves, you compare the hash code of the value. So you may have to do a calculation that way. It's sort of a trade-off between space and time. Is that right?
If I understand your question correctly, is you're saying that I'm not storing the hash code of the elements there. That's right, like for that performance numbers that I showed you here. So for example, the 5 times memory improvement is like without storing the hash codes or memoizing the hash code, to call it like that. But in the research paper about the jam data structure, I was going into detail in like different approaches, in like what does it take in like memoizing the hash code or not per element level. And there's also the second level is like if you store it and memorize it on a collection level. So there are different trade-offs involved, and all these different trade-offs can lead to different numbers of invocations of hash code and also equality, as you already like mentioned that like if you don't store it, then you have like probably more comparison of values that you can rule out otherwise. And but the nice thing is that the jam data structure, for example, it's likewise applicable to storing hash codes or not. And you can even do that like more efficient because on a node level, like aggregated, I can store the hashes for different elements, like in one int array, for example. And in my point of view, it's the best combination of what you get like from the Scala and the Clojure data structures, because Scala, for example, memorizes the hash codes in leaf nodes. So like in a Java util hash map, you have like one like entry, let's say, class that stores like key value and the hash code. And that already like adds up to a lot of like memory consumption. Whereas like Clojure doesn't do it, like similar to what I presented here. And you get essentially rid of like one layer of the tree, like all the leaf layers, because they're inlined one level up. And at that level, you can actually also like store all the hash codes of like the aggregated leaves there. So it's adaptable. I'm not using it like myself in that configuration, but like it's described and in the paper that I mentioned.
Thank you.
Right? More questions? Hesitations? Comments? Otherwise, thank you for your attention.